Hello. Hello. So it's a pleasure to be here. This is my second time in Turkey. So the first time was I came to a meeting in Marmaris, I think it was 2012. So I got back home, I told my wife, so I think Turkey is the most beautiful country I've ever been. So this time around, she didn't allow me to come along. She said she wants to come with me. But we had the deal, so she doesn't tell the children what she sees here, because then the children wants to come, this gets very expensive. So I'll give this talk. As you see, I won't have many equations, but we can catch up later if you want to see the details. So the talk will be about a typical problem in statistical mechanics. So think you have a really light body doing some really fast motion and a massive body, and they interact. So the question is whether you can transfer energy from the slow massive body to the light body. So this is a classical problem in statistical mechanics. I think if you open a textbook in statistical mechanics, probably you see this problem. For example, consider a gas. So you have here a cylinder and then you have a gas, so you have many particles. So what you do then, you slowly compress the gas. So what will happen, it happens that if you do it slowly, the particles will heat up, so they will become faster, the temperature will increase, and then you slowly bring back to the initial position, to the cylinder. So what happens here? So I had this initial position, I compress, then I increase back, what happens? So I think you all know what happens, so there is no entropy growth, and there is no heat transfer. This is one of the main achievements of statistical mechanics. So if this process is adiabatic, this means like as long as you do this process slowly. Yeah? So the main result I want to tell you here today is the following. So let me tell my main results now, and then I'll tell you how we get it. Is the following. So this process that you've seen, that we discussed, that if you do adiabatic work on the system, you do not increase the entropy. This holds for large systems. I will prove that for small systems, when the number of degrees of freedom is small, typically the entropy will increase and the energy will grow exponentially fast. So there is a big difference between large systems and small systems. In particular, you can use these ideas to create heating machines for molecules. So let me just discuss this, so why large systems are so different from small systems. So why there's no entropy growth in large systems. So if you speak to people so what's the basic idea in statistical mechanics? So if you open a textbook, they will say that the volume is conserved, right? So it's probably it's written your favorite statistical mechanics textbook. So first of all, this idea that the entropy does not grow is an experimental fact. If you do an experiment at home, you're going to see that there is no heat transfer. So the point taken if you do in a gas. But mathematically, the way you justify is the following. So think you have a Hamiltonian system, yeah, and the system depends on a parameter, as we've seen in the first talk, yeah? So then what you do, you slowly change the parameter. So think of the frequency of changing is very slow. And then you assume that for every frozen value of this parameter, the system is ergodic for the Liouville measure. Yeah? So if you do this assumption, there is one classical theorem in ergodic averaging theory that's called the Anosov-Kazuga averaging theorem. It says that you can write mean equations for these low variables. So think now, you have fast variables and slow variables. So the fast variables will be the momenta and the positions. They're changing really fast. But the slow variable now is the energy, because I'm doing this process quite slowly. So this theorem allows it to write an equation, a dynamic equation for these low variables. So this is what the theorem says. It says that any slow variable in the system, as long as the system is ergodic on every energy shell, can be approximated by averaging the fast equations over the Liouville measure. So this means like, so basically this is a reduction statement. Yeah? So you would have this huge phase space, and this slow variable will depend on this dimension of this huge phase space. You do averaging, you get a low dimension equation. So once you do it, the volume will be a slow variable, because the volume will be changing slowly as well. Then you can do corrections, and you can apply this theorem. You get that the volume is 0, so the derivative of the volume. If you introduce some notion of entropy, let's say Hertz entropy, then the Hertz entropy will be the log of the volume, so this means the entropy is also conserved. So everything's fine according to what we see everywhere. So now let me give an assumption. So if you see here in this Anosov theorem, we had this word here, ergodic. So what I will do, I will break this assumption. So I'll say that if I have a Hamiltonian system, I have a set of parameters, then for some set of parameters, the Hamiltonian has more than one ergodic component. Yeah? So this means like the Liouville measure is no longer invariant and so on. My other assumption is that I'll do the pumping the highest order term. So basically means like if you take the derivative of the Hamiltonian with respect to the set of parameters, this has to be proportional to the Hamiltonian. Yeah? So under these two assumptions, I can prove the following results. So, so first of all, the Anosov-Kasuga no longer applies. So you cannot claim averaging. So there is no barrier for entropy growth. So as you see, the system cannot, mathematically speaking, the system cannot increase entropy because you have this invariant, so that will be the derivative of the volume. And this comes through ergodicity. Once you break ergodicity, I mean, you're free to play your game. So let's play this game. What you need to do is to generalize the averaging theorem for the no-ergodic case. This is really hard, and many people doing, so we finally succeeded. The main results are the following. That if you introduce energy functional, so here's my energy functional. For systems with small degrees of freedom, this energy function is called entropy. You see, once I break ergodicity, it's really hard to define this function, yeah? So, but I'll define anyway. So this will be my function. And the main results are the following. So you see there's a log of the volume, and the volume is proportional to the energy. So if I have entropy growth, then I have exponential energy growth. Yeah? So linear growth of entropy implies an exponential growth of energy. So what we can prove using all this theory is the following. So if you do a period, so you squeeze the gas and you push it back, then what happens that after this cycle, this entropy will grow. So if you repeat the process, you get exponential growth of energy. And you can prove more. You can prove that the distribution of the log of the energy will tend to a normal. This means like the process is log Gauss. Let me give you one example here. So I have this result does not depend on the Hamiltonian. So this is generic on the Hamiltonian. So I'll take the Young-Mills Hamiltonian and I'll do some cycle very slowly. So here is the number of cycles I do. Here's the energy of the ensemble. What you see is the energy grows exponentially fast with the cycle. So here's log scale, here's linear, so I have exponential growth. So just to conclude, large systems, small systems, they're very different. For small systems, adiabatic process can transfer heat to the system. So you can have exponential energy growth. Thank you very much.